What a cute photo. Nice.
Yesterday, for those who missed it. Went over vectors. These are just three-dimensional floats. For example, if you want to set the position of an object to some place in the room, every location has a coordinate, and that coordinate is a 3D vector. Vectors can also represent directions, so you can set the rotation to face that direction, and it'll do that. There's really just a handful of chips you're likely to use. What's up, Sadie? Yeah, today we're going to be going over physics. So let me get out those chips. Okay, so if you go to the physics category in your palette, you'll see a lot more chips than this, but these are really the only important ones, and the other ones are pretty basic, like get camera position, nothing you haven't seen before. So basically, if you think about what we did yesterday, we were like moving objects around, like you'd set a position and the object would go there, and that's kind of what we do in physics as well. We use them we simulate like real world physics. The main things we simulate in a rec room are just like position and rotation, except that instead of manually picking a position or rotation to move that object to, we let the rec room physics engine pick those automatically. So like if I were to like take like a spawn in like a sphere and set it to physical, like configure it with my maker pen, set it to physical and drop it, you could like roll around. That's physics. So those kind of physics are just working on their own. You don't have to do anything, but there are also chips in Rec Room that you can use to manipulate the physics. Yeah, what's up, one? Collision data get normal. We'll get to that in a second. We're going to cover all these chips right now, actually, if there's no other questions. Cool. Okay, so the main ways that you manipulate physics in Rec Room are with like velocity and that's kind of we really only use velocity. I think there are like ways to set acceleration, but they're not too important. I'm not going to go over that here. And another way you can interact with physics is not like changing the physics of objects, but you can like observe them. So we have like overlap box, overlap sphere, raycast, sphere cast. These will allow you to check, like raycast, for instance, will send out a line and it will tell you what you're going to hit. So that's a very useful chip. I think we used it a little bit earlier. So starting here, we have velocity add. This, as the name would imply, just adds a velocity to an object. So you have the target, that's the object. I think it's a player or Rec Room object. We have a velocity port for meters per second. This is yellow. You'll see it's a vector. So just like we talked about yesterday, you'll get a three-dimensional vector and apply that to that object. There's a multiplier. This will scale up your velocity, and there's a maximum speed. So if you're already going really fast, it'll just like clamp it. Yeah, that chip's pretty straightforward. Velocity reflect. Not going to go too much into detail on this one because it's kind of similar to this one in that it will edit the velocity of an object with a direction, max speed, and multiplier. There is also a additional speed. It basically like reflects velocity like about some surface. We won't use that here. Velocity set. So similar to velocity add, which will change the velocity of an object, velocity add will take whatever current velocity you have and add this new velocity on top of it. So if you're going really fast in one direction and then you add a slight velocity up, you'll still be going really fast in that direction. You'll now just also be going a little bit up. Velocity set doesn't care what your current velocity is before you run it. After you run this chip, your velocity is just whatever you told it to be. It's some function of your previous velocity. And by the way, I suppose I should explain if anyone's not familiar with velocity. Velocity is just like, you can kind of think of it as speed, like how fast you're going, except it's directional. Like if you're going like 5 miles per hour, that's the speed. Velocity has a little bit more information. It includes the direction. So if you're going 5 miles per hour to the right, that would be a velocity. And the magnitude of a velocity literally just is the speed. So it relates very closely to everything we were talking about yesterday with vectors. Do you have a question, Wolf? Just hanging your hands up. Cool. Over here, these 4 chips are very useful for observing things in the world. Firstly, raycast, I think we used this a little bit earlier. You have a start position. This is a vector, just some position in the world. You have a direction. This is just like a directional vector telling it where to look. And then we have max distance. This is just how far it will cast the ray. A ray, you can think of it as a line, except instead of a line going infinitely in both directions, it has a starting point and then goes infinitely out from there. So that's why it's called ray cast. It casts a ray out from the starting position in the direction. And then what it will do is it will check for anything that it hits. So there is a bool output. The first one here, hit. This is true or false. True if it hits something, false if it doesn't hit something before it reaches the max distance. By the way, this is a float port, so you can configure it and literally just type in the word infinity, and it will understand what you mean and just use like an infinite value and never time out. There are a couple other ports, player and object. Only one of these, either 1 or 0 of these will be like not invalid. Like if I shoot out a raycast and I don't hit a player, this will be invalid player. If I don't hit an object, this will be invalid object. It just tells you what you're hitting. Distance is how far from the start position until the object that it hits, like the distance between there, just how far it goes till it hits it. Hit position is where it hits it. So this will be some vector 3 coordinate along the ray that you shoot it out, wherever it first comes into contact with the object that you hit. And surface normal, I explained a little bit what normal is yesterday. It's like the perpendicular vector from some plane. So if I shoot a ray against this wall, it doesn't matter which angle it's coming in, it's going to hit the wall and know that the normal to the surface is sticking straight out. So it kind of just tells you like the angle that it's hitting the surface. Below we have sphere cast. This is extremely similar. You'll see all of the outputs are exactly the same. Hit, player, object, distance, hit position, surface normal. They all work exactly the same as well, except that instead of shooting a ray, instead of casting a ray, it casts a sphere. So the window that it will like check for colliders in is a little bit bigger. You still have a start position, you still have a direction, but you also still have a max distance, but you also have a radius. So instead of just shooting out a straight line, you can think of it as like a circle almost. It's called sphere cast because technically it's a sphere. As you get like to the end, it will contact objects along the outer edge of that sphere first. Cool. So these ones both output those. Those are just objects. If you look above, we have overlap box and overlap sphere. These chips are very similar to each other, and they're kind of similar to these in that they will check for objects in some region of the room. They have a center, or at least overlap box has. Let's start with sphere because it's a little simpler. It has an origin. This is a 3D coordinate, just some place in the room. There is a radius. This is just the radius of the sphere. So if I put 1, it'll be a sphere with a diameter of 2, 1 meter out in each direction. And then there's an exec. So if I run this, it won't actually do anything until I run the exec. Unlike these ones, these don't have execution ports. They just run on their own every time you like access one of these output ports. But this has an exec. There's a collision. Like this has collisions, and you'll see that it's a list. And if I take out my maker pen and hover over the output, it is a type of list collision data. We haven't talked about collision data yet, but collision data, you can think of it as a type that includes a bunch of other kinds of information about the collision. So everything that this hits, unlike these ones, spherecast and raycast, these will just hit the first item they come across and then stop. These ones will run and they will get every collision within that sphere or box in this case and put it in a list. So let me talk about overlap box and then we'll talk about collision data. So this is similar to overlap sphere, except that since it's a box instead of a sphere, you still give it a center. This is kind of similar to origin. And then you give it extents. This is like how big the box is. So if I give it like 1, 1, 1, it would be a cube, like 2 meters in each direction. And then orientation. This is a quaternion. We haven't talked about quaternions in this class, and we're not going to. They're just a way to represent rotations. If you just like put down like a quaternion, create chip, and hook it up here, that's just like a non-rotated box. So that's probably what you'd want most of the time. And then they'll check anything within that area. So if I do overlap sphere, if I were to run this, center it in like the middle of the room, give it a really big radius, and then I run it, it would have a collision data for every player and every object in the room. So there'd be an entry in this list. Like for me, there'd be one for you, there'd be one for the floor. Also, you can configure these. All 4 of these chips here, all these 4, you can configure them, and there are 2 toggles on them. Ignore players, it's a toggle. If you turn that on, it'll just pretend the players are invisible. There's also one for ignore objects. If you turn that on, it will similarly pretend the objects don't exist, and when it's like running that calculation. But like, what actually is collision data? So let's talk about that. Over here, we have a few chips. So first of all, this isn't a list. So when you run it on the list, like, you have to get the specific element. So you just use it like a list get element chip, like we talked about before. And then you have your one specific collision data value. And this includes a bunch more information inside of it. So we have collision data, get distance, get normal, get object, get player, and position. So that one value is encoding all of this information inside of it. And if you want to access them, you use these collision data get chips. So if I were to run like overlap sphere, and for some sphere that like I myself am included in, it would return as one of the elements in the list a collision data representing that collision where it hit me. And then if I were to take that collision data and run get object, it would be invalid because I'm not an object, I'm a player. Get player would return the result of me. So this player port would be will chill. This position would be wherever it hit me. So like maybe my hand is closest to the sphere, and it would return the position of my hand. Get normal normally returns the surface of an object. I think in the case of overlap sphere, it's just a vector from the center of the sphere to wherever the position is. And then get distance, kind of similar to what we've talked about before, just how far from the center of the sphere to the player or object that it hits. And that was an example for me, but it's the same thing for objects. Cool. So we talked about those. Similar to velocity that we talked about over there is angular velocity add, angular velocity set, and get angular velocity. These work pretty much identically to the velocity chips over there, except instead of these traditional velocity chips over there, that is just like you set a velocity with some vector going forward, you just go in that direction. This is angular velocity, which means it's how fast you're like spinning. So if you're spinning around one axis pretty fast, you're going to have a high angular velocity in that direction. You'll see these are also vectors as well. So that'll give you the like, I think it's degrees per second along each axis that you're rotating. We have add and set just like the others, which work as you'd expect. They either add to your current angular velocity or set it ignoring the previous value. We have request velocity set over duration. This will update your velocity over time. So you'll see it has an exec, so you have to run it. It takes a target object. This is either a player or an object, a velocity, very similar ports to like set velocity. And then, but it also has a duration. So it will continue adding this velocity for however long that duration lasts. You can kind of use it to like ensure that something has a continuous velocity. We have a couple chips over here, get rotation, get velocity. I suppose also have get position here, which we've used before. Get velocity will take a player or object, give you a vector representing their velocity. So if I'm going up really quickly, the y component of this velocity vector will be pretty high. Similarly, if I'm going down, it will be the y component of that vector will be negative. No matter where I am in the room, because your velocity doesn't care about your position. It's just looking at how your position is changing over time. We have get rotation. This takes a player or an object, gives you a quaternion. As I mentioned earlier, not going to go too much into quaternions, but that's just a way to represent rotations. You can convert it to a vector if you'd like. And then we have a couple other chips, get position and reference object space, get rotation and reference object space. These are a little bit newer. They take a player or an object for both of them, and then a reference object for both of them as well. And they will give you the position, or in this case, rotation, of the object or player as if the reference object was the origin of that space. So Yeah, what's up, crypto? Yeah, that's all good. You can come in and out as you'd like. The videos are all on YouTube. So these will so like for instance, if I'm standing here, my position is relative to the world origin because that is just like the ultimate like starting point for the world. If I were to give it, for instance, some coordinate over here or some object over here, at like my distance, my position would not be as big as it is now because the origin point is a lot further than like this coordinate here. So like, my position would just be like I don't know, like half a meter or so in magnitude. Cool, and that's pretty much all the chips. Um, there's not a lot of chips for physics, at least not as many as we've seen for other topics, but you can do a lot with them. Anybody have any questions before we get to the example? Oh yeah, what's up, Wolf?
For requesting velocity, how does that usually will work, or what will, exactly will happen if you're requesting a velocity to an object?
Yeah, so I actually haven't used this chip before, so I'm not exactly certain, but my assumption is that you run it, and it would be kind of similar to editing the velocity on something like a 30 hertz, where it's going to keep applying it every tick.
Mm-hmm.
Um, like the physics engine, it's possible it's interpreting a little bit differently because there's a concept of like an impulse versus like actually applying it over time. Um, when you traditionally set velocity here, that's considered an impulse. It's just like an instantaneous, like like imparting of speed. This is a little bit more realistic. Like in real life, you can't just suddenly start accelerating in one direction because you'd have infinite acceleration, or just like infinitely start changing your speed. So this is a little bit more realistic. I think we probably made this for some RRO recently. Might have been Make It to Midnight.
Oh, okay. And overlap box, I tried using it before, but how does that usually work again?
Yeah, so you can think of it as you give it information to create a box. You give it a center,
Yeah.
like extents. This is just like the scale of the box in each dimension, X, Y, and Z. And then orientation, that's just like the rotation of the box. And then when you run it,
Okay.
it will take that box that you've created and it will look for any object or player, assuming you haven't disabled objects or players, and then look at the collisions for each of those inside of it. So for instance, you could use this to completely simulate a trigger volume because the trigger volume is just like a box and it keeps track of what's inside of it or outside of it. You could pretty much do the same thing, but instead of having to need an actual component in the room, you can just do it in circuits, and it's a little bit more flexible because you can just power like the transform of the box however you'd like.
What the? Oh, okay.
Cool, that's good. You can get started with the
Those are new
example now.
chips.
Which ones?
Give position, and give rotation is reference object space. That's all
Yeah,
new?
I think those are new. I actually haven't used those either.
Okay. Because I haven't seen it before.
Okay, so something you might see in rooms, which can be pretty fun to play with, is just like a gravity gun, which is what we're going to make today. So if you haven't seen something like this, basically imagine a trigger volume or gun handle, any sort of handle. You can take it and you can point it at a player, and you can click the trigger, and it'll pick them up. And if as you move the trigger around the room, it will physically like pick them up, like the player that you were pointing at, and move them so that they're staying in the same location relative to that handle. And we're going to make something like that today. This requires various things you've learned, including vectors, physics, and networking, variables, and other basics. So let's get started with that. Let's take out an event receiver. We're going to need 30 hertz because we want to continuously move the player. Cool. So let me configure this 30 hertz. So that's just going to run 30 times a second, similar to what we did last class. And then we're going to have some player that represents whoever we're holding. So let's take out a player variable so we can store the player in that variable. And I'll just name this held, whoever we're holding with the gravity gun. And I'm going to turn on synced because like if when I pull the trigger, obviously we don't have any of this yet, but when I pull the trigger, we're going to set the player that I'm pointing at to held, and we want it to be synced so other players know who it is. Because if you think about what we talked about in the networking class, we're going to be moving the player every time 30 hertz runs. And if we move the player, that is potentially a networked action. If I run set position chip on any of you, that's going to take up network heat because I'm not the authority player over any of you. The local player is always authority over themselves. So if I pick somebody up with a gravity gun and I try to move them every frame, that is going to run out of heat. If I pick them up with a gravity gun and tell them to move themselves every frame, that's not going to take up any network heat. So that's why we can do a little bit of networking up front, and then we can save ourselves from consuming unrealistic amounts of network heat once we actually do the operation. Okay, so let's take out if player is local invalid. So this chip here is a pretty good shortcut to check that the player, as the name would imply, is both valid and local. We only want to move ourselves, or the player who's being like held by the gun, if they are both the local player for the aforementioned reasons of saving network heat, and obviously if they're valid. If this is an invalid value, nobody should be moving themselves, so we won't run that. Cool. So that's just going to do some set. We're going to use add velocity there to move them toward the thing. Oh, it's called velocity add, not add velocity. Cool. So this is the main chip that's going to do most of the logic here. I'm not going to hook that up yet because I don't have the ports connected, so it would give errors. But the target we want to move is going to be the held player. So I can just grab that from the variable, hook that up there. We can figure out the velocity. The velocity is just going to be wherever they currently are, and we want to move them towards some point in front of the gravity gun. We don't have any of that yet, so let's set that up. Let's take out the trigger handle. I'm going to configure this object board and detach it, so as the board moves, it won't move with it. It's a little bit easier to follow. Cool. Okay, so when we pull the trigger, this is going to run primary action pressed, and when we release the trigger, this is going to run primary action released. So those sound like good places to set the held value to the player in front of you. And then we have to remember that when we release it, we want to let them go. So we'll update this again. We'll set it, instead of saying that we're going to set it to whatever player is in front of the gun, we're just going to set it to an invalid player. So let's take this chip and move it here. And we're going to hook up this exec. So when they pull the trigger, it sets the held value. We need to get the player that is in front of the handle now. So we can use the raycast chip for that. Let's take out a raycast. Okay, cool. So this has a couple more input ports that we're going to need: start position and direction. We can actually get all of that just from the handle. So if we want to, like, imagine if I have the handle and I pull the trigger, we want to pick up the player in front of it. That means the ray is going to be starting at the position of the handle. So wherever the handle is the start position. And the direction is just the forward vector coming out of the handle. So let me take out a couple chips for that. We'll just need get position for the position. And this self port on the trigger handle board is going to return a reference to the handle. So that's what I can connect it to. And then let's hook that up to start position. So that looks good. Now we need the direction. So let's take out a get forward vector chip. This chip will just give you exactly what we need. The vector coming out of the forward direction of the handle. Remember that the forward vector is the blue vector. So if you're wondering which like axis like you want to look at, if you configure the object, you'll see that if you configure it and go to like the move tool, for instance, you'll see a blue arrow coming out of the forward direction. So that's how you know it's forward. Cool, so that's all hooked up. Let me, just to visualize this, I'll take out a text component so you can see what this is hitting. Just so we can show the name of the player. Gonna unsync this so we don't all try to set the network heat. Cool. Oh, need the 30 hertz, of course. So let's hook that up. This is probably going to give a lot of errors because it is not pointing at somebody most of the time. So let me also configure object collision off on the raycast. So if I configure this chip, there are a couple toggles. I will turn off, or I will turn on ignore objects. So we only want to hit the players. Yeah, I should probably check that this is valid. One second. Oh, our max distance is still 0. So this honestly should probably default to a higher value, so you don't get bugs like that. Let me just configure this port and increase the max distance. I'm just going to type in 100. Cool. And now when I put it out my hand, it updates to will chill. When I point it at crypto here, it will update to crypto. So that's just how we know that it's working correctly. Okay, great. So we have the player. So we can just wire that directly into the player variable when we click it. So now when they pull the trigger, we're going to set this player variable and we're going to set it to whoever we're pointing at the raycast. Cool. If we're not pointing at anybody, this will be invalid. We'll set it to an invalid player. It will already have been invalid because we weren't picking anybody up, so that's not really changing anything, so that's fine. And down below, when we let it go, let's put down another variable, another instance of the same variable, and we'll set it to invalid. So let's hook up that exec. And if I click on local player here, this will switch to invalid player. So that's exactly what we want. We don't want to be referencing anybody when we let go of the trigger. Cool. So now what we need to happen is we want to save the distance the player is from the handle when we pull the trigger. So if I take the trigger and I point it at somebody and I click on them, we don't want them to suddenly change how far they are. We want to know how far they are from the trigger when I pull the trigger, and then as I move them around, they'll stay that far, which means we need a float variable, and we need to keep track of that distance as soon as I pull the trigger. So we can use a variable changed event. I don't think we've used these before, but they work just like any other event. I take out an event receiver, and I configure it, and if I look at held changed, cool. This event will just automatically run whenever the value in the held variable changes. Rec Room will just run that automatically. Okay, cool. So now we need to calculate the distance. Let's just take out a distance chip. That's a simple way to do that. And we want to look at the distance between the local player. Actually, for this gun, Like if I get the position of a player, that's going to give me the position like at their feet where they're standing on the ground. That could be a little bit weird if I'm picking you up and your feet are like directly in front of my trigger handle. So let's use torso position instead.
I'm super
Yeah, player
glad.
body position is the name of the chip.
Aw.
So let's take that out, hook that up to one of the ports. And then the other position we want is the position of the trigger handle. Cool. So that's telling you how far each of us is from the trigger handle. I'm about 1.7 meters away, so that looks good. And we're going to save this into a float variable. So let's take out one of those. And I'll rename this to distance. And for the same reason, we're making the held variable synced. We're going to make this one synced as well. Actually, we don't need to make this synced because we only need to keep track of our own distance. So like if I click on some player and that player, so when I click on them, we'll update the held value. And this is a synced variable, which means this event receiver held changed event will run for everybody in the room, which means we can all calculate locally our own distance from the trigger handle. Nobody's going to use their distance except the person being held. So if you cared about that, like if for instance you had this hooked up to another system that used a lot of heat, you could try to optimize that, but this is fine. So we'll set the distance. We're all going to keep track of how far we are from the trigger handle when we set the held player value. Okay, cool. That looks good. So let's hook this back up here. We can hook this up to the held value. So if the held player is valid and local, and we're still going to set the velocity. Now we need to calculate the velocity we're actually going to do. So let's take out. We want to do something similar to what we did yesterday, where we subtract two vectors to get like the vector pointing from one object to the other. So we're going to do the same thing here. Let's take out a subtract chip. And we'll subtract the position of the handle from okay, we actually have to do a little bit more math. So if you think about it, where do we want them to go? We want them to go to that position in front of the trigger handle. So we know where the trigger handle is. We know the forward vector. We know how far we want to go in that direction. So we can do something similar to kind of what we did yesterday, making the thing above your head, where we multiply some distance by a directional vector. My hand just died. 1 second.
Hey. Egg. Egg.
Okay, let's see how long this works. Okay, so we need to calculate the vector in front of the handle. So let's take out a few chips to do that. First, an add chip. We want to add the position of the trigger handle to how far we want to go in front of it. So first, we'll take just the position of the handle, and then we need to calculate the forward vector. I believe these are already normalized. Yeah, that looks normalized to me. And we're going to scale that by the distance. So let's take out a vector scale. Okay, so I just hooked up a few connections. Let me explain what that does. First, we have in the bottom port here, this is just the position of the trigger handle, right? So that sounds good. Up above, we are adding this other vector. This is the forward vector of the trigger handle, and we're scaling it up. The forward vector just has a length of 1. We're multiplying it, we're scaling it up to have the distance you are from the trigger handle. So if you're 10 meters away, we now have a 10-meter vector going from the position of the trigger handle to 10 meters in front of it. So this will calculate this output here at the end of this add chip. This will give you the vector, whatever distance it is in front of the trigger handle, and that's where we want to move the player to. Okay, cool. But there's one last step. We want to do the subtraction. So that's where we want them to be. If we take where we want them to be and subtract where they currently are, that will give us the vector pointing to where we want to set their velocity adjusted to. So let's just do player body position, same as we have over here. I'll go with player body position. On the top, let's subtract, and then we'll subtract. I think that's backwards. Let's hook that up on the bottom, and then target direction at the top. So this is the vector when we want to move them. Let's hook that up to velocity. Where is Doomman? Okay, looks like I have. Oh, I haven't connected it yet. Let me also increase the multiplier to something larger. I'll set this to like 20, just so it's a little snappier. Cool, and now you can see it's moving them around as I move the trigger handle. So as I turn it, it'll remember how far it is. You look like you want to be picked up default. There you go. I think my velocity might be a little bit too high. Let's turn it down a little bit. Cool. You could do some optimizations to prevent that wobbling. Yeah, I think the velocity is too high, but that's the general concept. Yeah, what's up? Do you have a question? Cool. So that is that whole example. Anybody have any questions? Cool. Okay, so we're going to move on. Oh, do you have a question, Crypto? Sure. Let me tell you what the assignment is first, which I'm going to do now. The assignment is we're going to make something similar to the example yesterday, that we're going to make something that follows you, but we're going to use physics instead. To do something kind of similar as I did here, we do the vector subtraction to get the direction from the object to. I'm not sure what's going on with that pistol, but good job, one. We're going to have an object that follows you. Do it with physics, so use velocity add. You're going to continually set the velocity add to push the object toward yourself. Do something similar to what you've done in the past, where you only do the velocity add if you were authority over the object, just like putting a shape, configure. Make sure you configure it and set it to physical. If it's not physical, velocity add won't do anything. Yeah, anybody have any questions about that? Okay, cool. And if you get that working and you want to do something a little bit more challenging, you could use angular velocity. So instead of just getting pushed toward you, it will actually roll. You can do that with the cross product of the forward and up vector, rotate it around that axis. But just work on getting like regular velocity working first. Okay, and then in a little bit, we're going to come back and I'm going to tell you all what the final is. Okay, everybody go get started. Okay, I'm back.